Okay, so here's the second part of practice exam number 4. I'm on question number 11, and they're asking about the data show the bug chirps per minute at different temperatures. Find the regression equation. So basically put this data in L1 and put this data in L2, and then you're going to go to your calculator and you're going to do the, write it over here, the linear regression t-test. So select that and choose the not equal to 0 option. L1, L2, not equal to 0, and then calculate. And when you do, you'll get your A value, which is right here, 36.115. Well, they want it rounded to 4 places, so 1157. And then the second, the B, this is A, and then B will be over here, will be 0.0454, rounded to 4 places, as they say. And now they next come and say, okay, what the best predicted temperature when a bug is chirping at 3,000 chirps per minute. That's an X value, right? These are X's, these are Y's. So the different amounts of chirps, X values, lead to different temperatures. How fast the bug is chirping tells us the temperature. These have a linear relationship. Now, the question is, remember there's 2 options when you're doing the linear regression t-test, and you get a regression equation, a line equation like that one. Sometimes you use that equation, sometimes you don't. So when the p-value is less than 0.05, use the y equals a plus bx, comma, plug in x. Because in that situation, as it says on the notes, there's strong evidence. When the p-value is low, that means strong evidence of a linear correlation. So it makes sense to use the linear equation. Now, what is our p-value? In this case, our p came out to be 0.007677. They never asked for it, but that is what it came out to be. And that p is low. That is below 0.05, way below. So that's a low p. So I'm going to use this equation. Now, on the last problem, number 10, when the p is greater than 0.05, there's not strong evidence of a linear correlation. So do not use y equals a plus bx. Instead, that's when you do the stat and calc and L2 and grab the x bar. Right? I think I left out one variable, but anyway, you look back to the last problem. That's where we do that. So let's finish up this problem. So in this problem, we're going to use this equation. So let me go over here. Y equals a plus bx. Now, when you use this equation, you have to be more accurate. Even though they asked us for 4 places here and 4 places there, I've got to use all the places that our TI calculator gave us on the screen. So for A, it gave me 36.1157. It actually might have given me more, but that's enough. And B it'll be 0.045 3780308, and then you plug in the x, which is 3,000, right? That's what they said right here. X is 3,000 chirps. Plug that in. I got on the calculator 172.2. That's degrees Fahrenheit, by the way. That's the temperature predicted. If you hear the bugs outside chirping at 3,000 chirps per minute, I'm not sure how you could count 3,000 chirps in a minute, you know the temperature outside is about 172 degrees. You must be on Mars or something. Don't step outside. So that's a crazy value. It's unrealistically high. It's outside the range. See, look, the chirps, the data we had, there was only crickets chirping. Highest was like 1240. So 3,000 is it's just not reasonable. So you can't really use this equation right here that we just used for 3,000. This is just an example of when you're going too far. You should only be plugging values into this equation that are in the neighborhood of the data we got. We only got numbers around 900 and 1,000, 1,200 as big as 1,200. So anyway, there's our conclusion on that one. So here we are with number 12. We're talking about randomly selected birth records, blah, blah, blah. So it's how many 35 babies born on Sunday, 58 on Monday, 57 Tuesday, Wednesday, Thursday, Friday, Saturday. Okay, what do they want me to test? Use a 0.05 significance level to test the reasonable claim that the births occur with, what does it say? Equal frequency. Equal frequency. What does that mean, equal frequency? Same each day. They're saying, hey, are there the same number of babies born each day? And they think, no way, 35, 50, that's not the same. Right, the data certainly, the sample data there, certainly don't look the same, but maybe that's just a little bit of luck. Maybe, looks pretty different to me, but we'll see. Let's do the statistical test. Now, what statistical test tells us that? Well, it's a goodness of fit. This is a goodness of fit. How do we know? We're saying, how well do these numbers, the number of babies born each of the different days, fit with equal frequency, meaning same number of babies born each day? Well, to do a goodness of fit test, you've got to have the observed, which that's already there. These are the observed numbers. That's how many babies were observed being born on the various days. And then you've got to also have the expected, like if there really were equal frequency and the same number born each day, how many would that be? So determine, when they say equal frequency, how you're going to do the expected numbers. The expected is going to be the total divided by the number of categories. So the total number of babies, divided by the number of categories, or in this case, days. So how many total babies do we have there? Well, if you add those up, I got 357 total babies were born during this week, Sunday through Saturday. So if they really had equal frequency, same number of babies each day, how many would we expect in each day? Well, you'd expect 357 babies divided by 7, right? Because the number of categories is 7 days. You'd expect 357 babies divided by 7, right? If they were evenly spread, you would divide by 7. That'd be how many babies were born each day. That comes out to be 51 per day. So in other words, 51, whoops, 51. That's how many babies we expected to have each day if really babies were born with equal frequency. That's what we're testing. Are they really born with equal frequency? So really what they want us to figure out is how good of a fit, right? Goodness of fit. How good of a fit is there between the observed numbers 35, 58, 57, etc. And the expected numbers, what we would expect if there was equal frequency, if it was same number of babies born each day, 51, 51, 51. So the null hypothesis on a goodness of fit test is always that the data, two data sets fit, that they fit each other. You think, well, no, they don't fit, they're different. Well, yeah, but that could be a little bit due to luck. How different are they? And the H1 is that they do not fit. That's always the null and alternative hypothesis. The null is that they fit, and the alternative is that they do not fit. All right, let's do the test. Move it over here. So two data sets fit and do not fit, and these are all 51s. These are the observed on the top here. And these are the expected down here. Okay, so what do? You put into L1 the top list, L2 the bottom list on your calculator, and then you select, well, it depends. If you have a TI-84, you will hit Stat, Tests, chi-squared goodness of fit, test, and the observed and the expected is L1, L2. And the degrees of freedom, that's going to be the number of categories minus 1. So in this case, how many categories do we have? We have 1, 2, 3, 4, 5, 6, 7, because there's 7 days in the week. 7 minus 1, so the degrees of freedom should be 6. So put that in and hit the buttons. Now, if you have a TI-83 and I gave you the program, then that's easy. Just hit PRGM, program, and then hit the chi goodness of fit program and hit enter, and it'll crank it out for you. So here's what I got when I did that. I got a chi-squared value of 13.490. I got a p-value of 0.0359. Okay, now what does that mean about our conclusion? Well, normally that p-value is pretty small, but they had us test it at a really strong level. They wanted to know beyond a 1% chance of luck. So this is actually greater than 0.01. So that p is not low enough. The p is not low. The HO does not go. We keep the HO. We keep that the two data sets fit. So we think, yeah, they fit. Even though these are a little different here and these are different there, we say, they fit good enough. At least there's not super strong. That's weak evidence, right? There's not super strong evidence. There is some strong evidence, but there's a 3% chance of luck, 3.59% chance that this data could have happened just by luck. That really, same number of babies born each day. We just got a little bit of a lucky data set where we had less babies on Sunday and less babies on Saturday. There's a 3.59% chance. That's just luck. So it's not strong enough evidence. We want evidence beyond a 1% chance. So we keep the null hypothesis, which says the two data sets fit. So fail to reject, there's insufficient evidence. Now what's really going on here? Really, look, the weekend, Saturday and Sunday, doctors that induce babies, and they can choose, by a C-section or just induce, they choose what day to bring the baby out, don't usually choose Saturdays and Sundays. They don't want to work on the weekend if they have a choice. So really there is strong evidence. It's just not, they wanted it so strong that we can't say it's beyond 1% chance of luck, but there was pretty strong evidence that there's not equal spacing here. The weekends are less because doctors are choosing when to induce Monday through Friday. not the weekends. So in the end of this study, we determined that the two data sets do fit weakly. There's a weak evidence that they fit. All right, on to the next one, number 13. So basically, we're doing Benford's law again, which says if you got a bunch of numbers, the leading digits, right? It's all about leading digits. So you investigate, basically an investigator. This is real life here. This is one of the ways they look for fraud. An investigator analyzed the leading digit from 782 checks issued by 7 suspect companies. So they looked at just the front digit, 782 checks. What was the first digit in the amount of the check for 782 checks? Benford's law shows that things like checks, the leading digit should be a 1 30.1% of the time, should be a 2 17.6% of the time, should be a 3 12.5% of the time, etc. It should fit with that. That's just what naturally happens as people write checks and as many other things in life happen. That's naturally how leading digits go. So if they're not fitting that pattern, we believe that there's some fraud perhaps going on. Well, so basically this is another goodness of fit, because we're trying to determine how the actual, in reality, they found out of the 782 checks, 249 had a leading digit of 1, 143 had a leading digit of 2, 89 had a leading digit of 3, etc. How well does that fit with what we expected from Benford's law, if there was really no fraud going on, if it was just like what naturally happens? So these are our observed numbers. This is what actually happened. What's our expected numbers? How are we going to calculate our expected? Well, in this case, the way you'll do expected, it's going to be the total number times the percent for each category. So it's not like the last one. The last one was all about equal frequency. Like we're saying the same number of babies born on each day. So we just took the total number of babies and divided by 7, because there were 7 categories, and that made them all equal at 51. They're not saying equal here. Benford's law does not say the leading digits are equal. There's the same number of 1s as 2s as 3s. No. It's saying there's a lot more leading digits of 1 than there are of 2 or 3. So it's not equal frequency. What we're expecting, Benford's law tells us that we should expect naturally what happens if there's no funny business is that you'll get 30.1% of all the checks should have a leading digit of 1. Well, how many is that? Well, you take the total number of checks, 782, times 0.301, right? You turn that percentage into a decimal, multiply that in your calculator, you get 235.382. That's how many checks we expect from Benford's law to have a leading digit of 1. So that's what goes right here, 235.382. And you got to use all this accuracy. So that's number 1. In fact, why don't I just write here's the expected numbers I got. So I got the 235.382. So for the next one, I took this percentage, 0.176, times the total. Here, I'll take the total number of checks, 782, times 0.176, and I got 137.632. Then I took the total number of checks times 0.125, next category, and got 97.75. So I'm writing out how many checks I expected to be in the various categories if Benford's law was really being followed. Next category, 782 times 0.097, I got 75.854. Next one's 782 times 0.079. I got, what did I get, 61.778. Next one, 782 times 0.067. I got 52.394. Next one, 782 times 0.058. I got 45.356. Next one, 782 times 0.051. Got 39.882. And last one, 782 times 0.046. I get 35.972. I know your calculator won't take all those digits. It'll take most of them. So now it's time to put the data in. So this data, the observed data up here, that's L1. And then these numbers here are L2. So put L1 and L2 into your calculator. And remember, the goodness of fit, the null is always that the two sets fit, and H1 is do not fit. So go through, do all the rest, just put in L1 and L2, and you should be able to get the conclusions on that one. I'm going to go on to the next problem. Okay, I skipped number 14. I'm just going to wrap up with number 15. 15 is the same as 14. They're both the same. 14 and 15 are both test for, what do you think? Where does it say? Use a 0.05 phosphorus level to test the claim that the amount of smoking is independent of seatbelt use. Test for independence. So that's what we're talking about here, independence. Now, what do we mean independence? Let's go to the next screen. We're talking about the number of cigarettes smoked per day and whether people wear their seatbelt or don't wear their seatbelt. So the theory is, hey, maybe the more people smoke cigarettes, the less often they wear their seatbelt. That's what we're wondering. So are those variables dependent or independent? So the idea is that maybe people who smoke more are less concerned about their health and thus don't wear seatbelts as much. Right? So as you go up the line in smoking, more and more smoking, maybe you'll get more and more who don't wear seatbelts. Doesn't look like the data is agreeing with that. Like right here, people that smoke 15 to 34 cigarettes a day, 47 wear seatbelts, 34 don't. So the question is basically, is this variable and that variable, are they independent? Meaning, do number of cigarettes smoked affect whether you wear your seatbelt or not? Or do they have nothing to do with each other? Independent would mean they're not related. In other words, how much you smoke has nothing to do with whether you wear your seatbelt or not. That's what we're wondering. Does how much you smoke have something to do with wearing seatbelts or not? Or are they in no way related at all? They're independent. Okay, so this is a test for independence. That's how you recognize this on the exam. They'll use the word independent. Test for independence. Okay, so how do we do it? Well, basically, we have to put this information, let me put it on a fresh screen here again. We have to put this matrix right here into your calculator. How do you do that? Well, you hit second matrix, and that gets you to the matrix menu. You go over a couple of times to the edit menu, and then you hit enter. And then you do the size of the matrix. This matrix, you always have to go down and by across. So this matrix is 2 rows down and 1, 2, 3, 4 columns across. It's a 2 by 4 matrix. So hit enter, put those in and hit enter, and then put in the matrix the 189, 14, 47, 8, 140, 20, 34, 8. Put that in. And when you hit enter with each entry. And when you're all done, hit second quit on your calculator. So you once you hit second quit, it's all saved. Well, actually, every time you hit enter, it saves that entry. So they're all saved. Hit second quit. Come on out of there. And then you'll just hit, when you're all done with that, you'll hit stat, and tests, and chi-square test. So not goodness of fit, just plain chi-square test, because this is test for independence. This is not goodness of fit. So chi-square test, and hit the buttons, and what you should get, here's what I got. I got a chi-squared value, 3.6. I actually got 3.680. I've noticed that the TI doesn't always agree with the answers on Math Excel. It turns out this is supposed to actually be a 1. Math Excel says 3.681. So you have 3 guesses. So if it's giving you a hard time and you're putting in some answer, try rounding the last spot up by 1. It's not coming out right on my calculator. I'm not sure exactly why. There seems to be some discrepancy between the TI calculator answers and what Math Excel wants. So I got 3.680. They told me they want the answer 3.681. So it's never off by more than 1. You have 3 guesses, so you can get it right. If you type an answer in, it says wrong, try going up by 1 or down by 1 in the last spot. You'll get it by the 3rd guess. The p-value always comes out right for me, 0.298. So what does that mean then? Is that a low p, high p? That's a high p, huh? Greater than 0.05. The p is not low. The HO, therefore, does not go away. So we keep the HO. What was the HO? Oh, I never wrote the HO, did I? I should write that back here. The HO for test for independence. Oh, here I'm going all over the place with these screens. The HO, the null hypothesis, well, let me go back here. The null hypothesis is always that they're independent. That the 2 variables, smoking and seatbelt use, are independent. H1 is that they're dependent on each other. They're not independent. So the 2 variables are independent. That's always the null hypothesis for test for independence, problems 14 and 15. So where is that one? There it is. The amount of smoking is independent of seatbelt use. Amount of smoking is not independent or dependent. There it is. So there's that one. So what we decide? We are gonna the P was not low. The HO does not go. So we're keeping the HO, right? The HO does not go. We're keeping it. So we're keeping the HO. We're keeping this right here, which says the amount of smoking is independent of seatbelt use. Right. Seems like smoking has nothing to do with seatbelt use. They're independent, no effect on one another, which means, is this theory supported by the data? No. The theory that, that a plausible theory is that people who smoke are less concerned about their health. No, the data doesn't seem to bear that out. It seems like seatbelt use and smoking are independent of each other. There we go.